Project number 2 of control systems that you will have to do. And this project relates to plotting the root locus of a specific control system that user is going to enter. So start with putting your name as and project name and date and all those things. Make sure you use clear and CLC to clear all the memory contents and clear the command window if you need, but clear is more important, CLC is not that important. Okay, so user is going to give you 1 plus kjs. User is going to give you the numerator and denominator of js as vectors, right? So you are going to ask user to enter the coefficients of the numerator and denominator of js as vectors, and then you are going to change the value of k from 0 to a large number, and I'm going to show you a sample, and I'm going to run it in front of you as well, the program that I made. You're going to change the value of k from 0 to a large number, and in my example that I put in this, I'm changing k from 0 to 1000 with an interval of 0.1, so I can have a smoother graph. It's calculating many roots. And then every time you change the value of k, what you're gonna have? You're gonna have one polynomial, 1 plus kjs. So let's say k is 10. So you're gonna have 1 plus 10 times whatever js is based on the numerator and denominator. That's one polynomial. So you will calculate the value of this equation, right? This polynomial, s plus pj, which is the denominator of js, times 1, of course, s plus pj, the product of all those poles, plus k, s plus zi, product of all the zeros, is equal to 0. So you're going to use this equation, and you are going to calculate the root each time you are going to change the value of k, right? And basically your root locus is what? Root locus is the collection of all those roots on the s-plane, the roots that you are calculating from the characteristic equation. When you are changing the k, every time you change the k, you calculate the root, and then you put those roots on the s-plane. So as you are changing the value of k, you are calculating, for example, if you have third order polynomial, that means every time you change the value of k, how many roots? You're gonna get 3 roots. So every time you change the k, you're gonna get 3 roots. You're gonna put those 3 roots on the s-plane, right? And once you are done with changing the value of k, then you have the collection of all the roots on the s-plane, and that is the root locus. To find the values of roots, of course, you can use roots function. And let's see, there is also a built-in function actually, which is called Root-locus. It is built in MATLAB as well as in Octave. MATLAB output is better than Octave though, as you will see. But the program that we are making, and I'm going to give you hints as how you're going to do that, you're going to get really nice output, as you can see in this sample. And actually this, I just built it, and today, I mean, I have this program that I built long time ago, like 6, 7, 8 years ago, but I modified this program today such that I get very neat different colors to show me that where the root locus is starting for that section and where it is ending. So different colors show you different sections of root locus, and you get the similar graph in MATLAB if you use Root-locus in MATLAB. Anyways, let's come to this example. This is one of the examples that I discussed over here as well, and I was referring back to that over and over again when I was discussing the notes. And this example is, let me figure out right here, I think this is it, perhaps, no, right here, this is example, right, that I discussed when we were discussing the nodes. So this is my input. When I run my program, it's gonna ask enter the coefficients of numerator of js. This is js, so numerator coefficients are 1 and 1, and then denominator coefficients, when I solve this, it's gonna be 1, 10, 32, 32 and 0, right? if you don't want to solve it, you can just put what? You can put poly from these roots, poly 0, -2, -4, -4, and it's going to create the polynomial with the coefficient 1, 10, 32, 32, 0. So whichever way you want to do it, I don't care. Okay, and then this will be the root locus. So let's discuss this in light of our 7 steps. Okay, so first step is to put to identify zeros and poles of J of S or F of S. So we have 4 poles, we have 1 0, 0 at -1, so I put 0 with O, and then I have 4 poles, 0, -2, -4, -4. So 0 I put with X, -2 I put with X, -4, -4 I put with 2 X's. Of course they overlap each other, so you don't see 2 X's, you see only 1 X. The second step was we have to identify the sections on the real axis which are part of the root locus. This is one section, number of root are odd on the right side. This is the other section, number of roots are odd on the other side, on the right side. And this is the last section, number of roots are odd on the right side. Step number 3, we have to find the asymptotes along which the zeros will be located at infinity. And we know that since there are 4 poles and 1 0, that means 3 poles are located at infinity, and we're gonna find those. Of course, when you are using MATLAB, you don't have to go through all the steps. All you are doing is changing the value of k, and calculating the roots and putting those roots on the plot, right? So we found that these are the asymptotes. This will be I don't know, 45 degrees perhaps, -1, -45 degrees, 45 degrees, or 60 degrees, -60 degrees. That looks like what? It looks like perhaps 60 degrees, and then 180 degrees. So I'm assuming it's 60 degrees, 180 degrees, and -60 degrees. We'll discuss this in that example, so you can refer back to that. The fourth is going to be where it will cut the y-axis, that is what will be the value of k that will result in the critically stable system, and then we find that value using Root-Hurwitz's criteria, create the Root-Hurwitz array as we did, and then this will be the value right here. This is the 0 line, I'm assuming. Yes, this is the 0 line. And the fifth step was find the breakaway point. So this will be the breakaway point. Again, when you have the graph in MATLAB, of course you can just hover over your mouse and you can see all those values, and you can confirm those values. If you're drawing it with your hand or calculating the values, you can confirm that your values are correct or not. And the sixth step is going to be, it's not present over here because we don't have complex poles or zeros. So sixth step is not present, and seventh is to put all of them together. Okay, so let me give you some hints as how you're going to do that. Before I do that, just for the comparison purpose, I'm also putting the root locus from the built-in function of Octave, which is called R-locus. This is how you're going to use it. First, you're going to create the transfer function from the polynomial, and then you're going to use R-locus of this system, and this is going to be the root locus. Now, it is not showing you that everything is in blue, so you don't really know what are the sections, where it is starting, where it is ending. Of course, this section is pretty evident, and this is pretty evident because it's going to start from here and it's going to go all the way over here. And from here, you don't know if this one is turning down or turning up and what's going on. And likewise, this one is turning down or it's going to turn up. So if you have color section, then it will be easy to identify which sets of roots are going where. And MATLAB actually produce color lines, like I'm producing colored line. And this is the first time again I produced today. I modified the program and I figured out how to produce the colored lines, or how to plot each specific section separately, that is. Okay, so how did I do that? The way I did that is when I'm calculating, so of course I'm using a for loop and I'm changing the value of k from 0 to 1000 in the steps of 0.1. Now every time I do that, but before that, the first thing I did outside that for loop, I just calculated the roots of numerator and denominator, and I just marked those down on the graph, and I'm going to hold on to the graph. So this I'm doing outside the first for loop. So in my first for loop, I went ahead and I calculated. I ran the value of k from 0 to 1000, interval of 0.1, and then I created the for loop, and I went through the for loop, and each time the for loop is changed, I change the value of k, and then calculated the roots of this equation using the roots command. Now when you use root command, it will produce the roots in a column vector, right? So if I go to my Octave and I do roots of 1, 5, 8, 9, 10, 23, 55, 67, whatever. So it is going to, oops, I forgot to put this. It's going to, what's going on? Let's see, did I put bracket over there? Alright, so it's going to produce a column of roots, right? So what I did today, before I just used to create a vector of all the roots and then plot it. So that plot used to be like, you know, the R-locus of Octave, all the blue one. But what I did, the change that I made, basically, first I converted this from column array to a row array by using the transpose of the vector, right? And then each time I calculated the root, I keep appending that row array. So for example, if I have transpose, so I have, this is my first root, this is my second root, third root, fourth root, fifth root, and sixth root, right? Now when I change the value of k next time, I will get 6 more roots. So I went ahead and I appended this vector, so I will have a second line of 6, and then I will have a third line when I change the value of k again. So this vector, when it will be done with all the values of k, this vector will have 6 columns, and it will have the number of rows based on how many times I ran the for loop, right? So then when you are plotting on S domain or S plane, sorry, you need basically, what do you need? If I go back, let's say this is your point that you're plotting, that means you are plotting x versus y. That is you are plotting the real part of the root versus the imaginary part of the root. So what I did is I used the MATLAB function real and imaginary, and I applied on this, and I created 2 separate vectors, or two separate matrices. One matrix with the real part of each root, and one matrix with the imaginary part of each root. When you use imag, it's just going to extract the value. It's not going to extract I, it's just going to extract the value, the imaginary part. So now I have 2 matrices from this matrix, one with all the real numbers, one with all the imaginary numbers. And then I took the first column of the real and the first column of the imaginary, and I plotted against each other. That's one of my section, and I'm holding the graph. Remember, I'm not gonna release the graph until I'm getting done with the graph, and then I'm gonna apply hold off. So I'm holding the same graph, and I'm doing this, I'm plotting this again in a for loop. So I ran the for loop, I took the first column of my, let's say, real matrix and first column of my imaginary matrix, plotted. Then the next value of for loop, I took the second column of real, second column of imaginary, plot that. So I will run the loop for how many times? The number of times I have the polynomial order. So I have 6 order polynomials, so I'm going to run that loop for 6 times. And each time I'm going to run the loop, then I'm going to grab the corresponding column from the first matrix, real matrix, and corresponding column from the second imaginary matrix, and plot those 2 columns against each other. That's going to give me one section of Root-locus. And like so, that's how I'm going to plot all of the sections of Root-locus. And since you're plotting them in the same graph, but you're plotting different vectors, is going to automatically change the color. So you don't have to change the color, it will automatically change the color. So when I plotted that, it changed the color. In this one, of course, I have only 4 sections because the number of polynomial at the denominator is 4. The highest power is 4, so I have 4 sections. So when I plotted each column of roots, real and imaginary, it created 4 different colors. So I have this blue, I have this, and finally I have dark blue over here. So that's how I plotted this. So hopefully it sounds a little difficult, but it is really not that difficult. You have to sit down, think about it a little bit, but it is not very difficult. You will figure it out how to do it. Let me do a live demonstration in front of you. Let's see, I'm gonna go and I'm gonna take that example, the last one that I discussed, this one. So let's take this. Okay, so this is my j of s, 1 over s plus 4, s plus 4 minus j4, s plus 4 plus j4, or this right here. So let's go ahead and plot this. I'm gonna run this, and so numerator is 1 and denominator is 1, 12, 64, 128, and since there is no constant, I'm going to take a 0. Takes a little bit, my computer is slower and I'm plotting a lot of points, so it's going to take a little bit. Okay, here you go. Nice. This is what we discussed, and observe. This is how it's going to look like. So this is one section, as you can see, purple. This is another section, yellow. Of course, there's a third section and fourth section. So we have 4 sections. And each color shows that how the roots from each pole is going to progress towards the 0. Remember, roots start from pole and they progress towards 0. And since we have 4 zeros sitting at infinity, then each of the pole will curve towards one of the zeros that is sitting at infinity. So this is how it's going to look like.